In this video, we will try to understand stress strain curve for some material P. Just to save time, I have drawn a sample stress strain curve. Let us assume that this curve is for material P. And if you will get a similar curve, maybe the shape, the overall shape would be same. Maybe the lengths of these various parts might be different, but we would get a similar curve for any material. Our material is material P, and this is the stress strain curve. What we are going to focus on in this video is try to understand how this particular graph is obtained and what is the interpretation of various parts of the graph and why this particular shape. To understand that, first let us try to look at how this graph is obtained. Right? So we take a thin wire made up of material P, and let us say this is the thin wire of material P, right? And then we attach some weight to this. Say for example, this is the weight attached to this, W weight. Let us say this has some particular length, let us say 100 centimeter length. Right? So I attach a weight to this and I measure the elongation. From these values, I'll be able to find out stress and strain. Right? So my first reading of stress strain. So I can find out, I'll get some particular value over here because I know how much weight I have at, and let us say this is 72 Newton. 72 Newton divided by this cross-sectional area will give me some value of stress, let us say some value x. Based on this particular value, I can find out the value of strain. What is the elongation, and I can find out strain. Let us say I get, let us call this x1 and let us say this is x2. So I get a value of strain. After taking these readings, I remove this weight 72 Newton. When I do that, the wire will go back to its original length, 100 centimeter. So I make a reading, I make a note over here. I'll write over here, elasticity. If it goes back to its original dimension of 100 centimeter, I'll put a tick mark over here, meaning that the object has shown the property of elasticity. After that, I'll increase the weight maybe to 80 Newton or whatever, maybe 82 Newton. I'll increase it by 10 Newtons every time. So here I'll get x3 probably, which would be equal to, I'll calculate this based on this force and cross-sectional area, and I'll have strain x4. And again, I will remove 82 Newton weight and again check whether it goes back to its original dimension. If it goes back, yes. If it doesn't go back, across. And I'll get such readings. And let us say that I keep on adding this weight of 10 Newton for a very long time, maybe infinitely. Right? When I do this and when I take these readings and when I know whether this particular wire is showing the property of elasticity or not, based on these I can plot this graph. So I have value of stress, I have value of strain, x1, x2, I can get a graph on this. And what is observed is that we get a graph of this particular shape. I have shown this graph in two particular colors. Part OB I have shown as green color and part BES shown as red color. Let us look at this graph closely. Basically, when we look at any part, we will be looking at two things. One is stress proportional to strain? And the second part is whether the wire is showing the property of elasticity or not. So these are the two things I'm going to focus on while I look at this particular graph. And let us say I look at part OA, part AB, part BD and part T. Now if I look at part OA, which I have shown in green color, part OA is a straight line, right? Which means stress is proportional to strain. When we have a straight line, the terms which are there on the x-axis and the y-axis are proportional to each other. So stress is proportional to strain. So I'm going to put a tick mark over here. What is observed in this part is also, which of course cannot be shown on this graph over here, but these experiments reveal that in the part OA, elasticity property is, this particular wire exhibits the property of elasticity. Right? So I put a tick mark over here, meaning that it goes back to its original dimensions. If I look at part AB, Now instead of being a straight line, it is becoming a curve, right? You can see it's curving over here. And therefore we can say stress is not proportional to strain. Meaning that for the same value or for the same increase in stress, the increase in strain is not uniform. It keeps on increasing, and therefore we say they are not proportional. This does not mean strain is not increasing. It is increasing, but it is not increasing proportionately. As part AB is concerned, there also it is observed that the wire exhibits the property of elasticity. So put tick mark over here. If I look at part BD, right, I can see that stress and strain are not proportional. You can see it's a curve, it's not a straight line. So I can easily put a tick. I'll use the red color over here for this particular part. So cross over here. And it is observed that from B point onwards, the property of elasticity is not observed. Meaning that when I remove this weight, the wire does not go back to its original shape and size. Okay, let us look at part DE. In part DE, again it's a curve, right? But it's going down, right? It is going down. That means stress is decreasing. I'll explain it when we come back to this part. Right now I'll simply say stress and strain are not proportional. Elasticity is also not obeyed. Okay, with this knowledge in mind, let's now look at these graphs or these particular parts more closely. In part OA, stress and strain are proportional and elasticity is observed. This is the simpler part, straight line curves, directly proportional relationship and elasticity observed. As far as part AB is concerned, here elasticity property is exhibited, but it's not a stress, they're not proportional. So in this particular part, what we say is that here Hooke's law is obeyed. In this case, they are not proportional. So Hooke's law is not obeyed. And the property of elasticity is shown over here. Since in this particular part, elasticity is observed, this particular part is known as the elastic region. And in this particular part, since elasticity property is not displayed, this is the plastic region. So the red color graph, this is the plastic region, this is the elastic region. Elasticity displayed, elasticity not displayed. Okay. Let's move further. Okay. At point A, Hooke's law is obeyed, right? Between O and A, Hooke's law is obeyed. Therefore, the stress which is associated with this particular value of A, right? This particular value, the stress that I get over here, this particular value of A. So the stress associated with point A is known as the limit of proportionality, because stress and strain are proportional in this region. So till this value of stress and strain show proportionality. As far as point B is concerned, right, till this particular point, stress from this particular part, they are not proportional, but they show the property of elasticity. So the stress which is associated with point B, this value of stress, is known as the elastic limit. Because in part OB, elasticity is displayed, elasticity properties exist, so this elastic region. And this is the elastic limit, the limit up to which elasticity is observed. So these are the two terms that we have introduced. And point B is known as yield point. Because again, after point B, elasticity is not displaced. Please note that here A and B, these are not the points. This is the stress connected to point A, stress connected to point B. Whereas this is point B. The point B itself is known as yield point. Okay, let's move to the next part, part BD. In part BD, elasticity is not displayed. That means if I take up any particular point in this particular region, let us say point C. After I remove the load, right, the way I removed 72 Newton and measured the original dimension, the wire does not go back to its original dimension. Maybe instead of 100 centimeter, it becomes 100, or it retains its length to 100.01 centimeter. Therefore, what we say is that there is some amount of strain. The strain is not zero. If it would go back to its original dimension, the strain is zero. But if it doesn't go back, there is some amount of strain. Maybe some amount of very minimum value of strain is there. And therefore, with point connected to C, there will be some amount of strain. Similarly, with some point connected over here, there will be again some amount of strain, maybe slightly more than this. So some amount of strain is retained, and that is known as permanent strain, because even after removing weight, the wire is not able to go back to its original dimension. And therefore, we say the property of elasticity is not exhibited, and therefore the plastic region. When the stress reaches the value of point T, so the stress has now increased, stress is going up. So when we reach this particular value of stress at T, what we observe is that the wire now starts thinning down. That means the stress has reached such a high value that this wire thins down and starts breaking. So its diameter decreases drastically, it thins down, and in fact it becomes something like a viscous liquid and it starts breaking off. And therefore this particular stress, the stress connected to point D, I will write it over here probably, the stress connected to point D is known as breaking stress. So this particular value of stress is breaking stress. Here the wire starts breaking off. And what is observed is now, since the wire has started breaking off, it has started thinning down, even if we decrease stress, even if we remove the weights, it is not able to go back to its original dimensions. Right? It continues to thin down. Right? The strain keeps on increasing. It becomes thinner and thinner. Its length increases. It continues to elongate. It is becoming thinner and thinner. It has become a viscous liquid. And as the stress is decreased, right, at particular point E, it breaks off. That means we don't have this wire anymore. It has broken off, and it happens at this particular stress. This is how any substance behaves when it is subjected to forces continuously and it is subjected to stress. The shape of this particular graph will be like this, right? It will have portion OA, AB, BD, and DE. The only difference is that for different materials, the length of these particular regions would be different. And we will see that in the next video as to how the length of these particular parts, OA, AB, BD, DE, differ for different types of substances like ductile substances and brittle substances. Thank you.